which I work at Duke Energy as a manager of emerging technologies, and also currently I'm a PhD candidate student at North Carolina State University. Today's presentation is going to revive the lessons learned from the design, building, commissioning, and operation of Duke Energy's Mount Holly microgrid. Everything that I'm going to show you today is pretty much the product of what we have done in the last 3 to 4 years. And all of the stuff that you see today is actually has been field implemented, tested, etc. So just to give you an example, a little bit about my department, we take a look at technology at about 3 to 5 years out. We do the testing, we do pilot projects, etc., try to understand pros and cons, and then later on we transfer it over to the business. We have been doing this for almost 12, 13 years. And we are in the arm of Duke Energy. So when it comes to research objectives for the microgrid that we started back in 2015, there are several different parts, right? So the first thing that we needed to do was to design the microgrid energy resources. So pretty much that was my job. Then we had to understand the grounding requirements. It's probably one of the most misunderstood parts about the and probably one of the most challenging parts when it comes to designing the microgrid. This particular microgrid has seamless islands to do that. Then there's going to be a section on the rate of change of frequency. I'm going to show you how we detect islanding, what elements do we use inside the relay. Probably the most challenging part with the distributed energy resources that are inverter-based is inverse current mitigation. We're going to talk about that. And then once when you have microgrid, how does the microgrid operate? We have also protection and control in island and node, which is, excuse me, probably one of the most challenging topics because inverter-based DERs do not produce a whole lot of fault currents. So sometimes those fault currents can be within the range of high load currents. Something similar that you have on the sub-transmission system when you have a long line and essentially you have a fault all the way in the back of the feeder. How do you discriminate between the fault currents that are low and high loading? Okay, I have been trying to advance the slide, but it's not doing. Okay, here we go. I'm going to be talking about next one, difference between seamless islanding and the black start. This is probably one of the most challenging parts. How do you operate microgrid? Do you do seamless islanding or do you do black start or do seamless islanding? I'm sorry, I'm trying to advance stuff, but it's not advancing in my screen. All right.
Hey, Alex. Looks like there is some kind of a feedback on the phone. I see that you are calling in from a different device. So if you don't mind holding for 1 second, let me change the setting here to see if I can mute everyone and then just not you.
That'll be fine. Can you hear me?
Yes, we can hear you now, and I think I got the setting done. So sorry for the interruption. Please resume.
No problem. Just want to let everybody know that for some reason I cannot see my slides advancing, so I've been clicking a few times. Okay, the last one, second to last one will be grid resynchronization, and what are we doing about the future research, right? So just for everybody to understand, this is our pilot feeder, right? There's a substation that has a supercapacity storage system, right? So we have a system that we have put in 2 or 3 years ago that has a battery plus supercapacitor, and the idea is to use supercapacitor for some fast response and the battery for some slow response. There's a recloser somewhere in midpoint. We have a voltage regulator, and there's a 1.2 megawatt solar farm on the feeder. Our microgrid is located right next to the 1.2 megawatt solar farm. So for those of you who have not had a chance to see Mount Holly microgrid, I have a video over here. Let's see if this is going to play. So okay, it's not playing. I apologize. Let's see. We got the. Okay, so this is Mount Holly microgrid. I'm going to be talking about different pieces and parts. This is the microgrid yard. On the left side, there is a four-way switchgear. There's a point of common coupling associated with the relay cabinet. Four-way switchgear essentially is used to, number one, we have way one, which is the point of common coupling. We have way two, which is connected to the transformer that transfers 1247 kV over to the 480 volt system. We have way three that is tied to the grounding transformer, which is probably the most critical part of the probably the most critical part of the microgrid. There's a AC coupled battery, which is the battery energy storage system that consists of the inverter and the battery. There is a connection between the PCC relay and battery energy storage system. There's this line that says DIDO, which is probably the most critical part for ensuring the seamless transition. So that is inside the microgrid yard. So as you can see over here, we have AC coupled battery inside this yard as one of the distributed energy resources. Then the second part of the microgrid yard, we have a PV system with a DC coupled battery. So it's a 150 kW PV farm with a 100 kVA PV inverter. Within this particular farm, you probably know there's an inverter loading ratio. That in North Carolina is between 1.2 and 1.6. And then we're going to talk about it later on. And then we do have a DC coupled battery energy storage system, which is actually 240 kilowatt, 122 kilowatt hour battery tied through the 250 kW DC to DC converter to the DC bus. We also have a 9.3 kilowatt DC system that is going directly into our ETO research building on the right and electric vehicle charging stations. The DC system actually enables 400 volt DC bus that is inside the research building. So when we do the islanding, we essentially take our building and we operate our building in island mode. And then the latest two additions, you can see 450 kVA generator. We were currently last week doing the commissioning, so this is during the commissioning. And we also have two 65 kW turbines over here. So essentially, the only thing that's missing over here is the 480 volt switchgear that's coming probably within the next 2 to 3 weeks, and we will be commissioning these two 65 kW turbines. So as you can see, we have 5 distributed energy resources over here. Natural gas generator, micro turbines, which is inverter-based, AC coupled battery, which is inverter-based, PV system, and DC coupled battery. So that's pretty much what we have inside the yard. For those of you who wanted to see how this whole thing looks like on the electrical and communications line diagram, you can see over here, excuse me, there's a substation that comes to the point of interconnection, which is the recloser where everything goes over to the distribution control center. And then in order to separate and create a microgrid, it's a 4-way switchgear that you see over here. It's a way one of 4-way switchgear that we open. On this particular picture, you can see 2 IEDs are pretty much relays. Recently, we have changed this stuff. So now, rather than having 2 relays, we have 1 relay that controls everything. There's a grounding transformer with relay number 3. There's a AC coupled battery, and you can see out of way 2, we go through the transformer to create 480 volt bus. That's where we have a DC coupled battery, micro turbines, generator. We had a second battery energy storage system that we have since removed, and we're looking for something else to put in there. You also have a communications diagram over here. You can see microgrid controller. You can see Ethernet switches, clocks, and how everything is connected. Okay, so when we started doing this stuff back in 2015, right? Distributed energy resource design, and this is something that I have taken a look at during my PhD thesis and conference presentations, right? Here are the 3 things that you have to pay attention to when you do the distributed energy resource design, right? When you have PV system as the only DR within the microgrid, there's a particular behavior that is different when you do the simulations versus the devices that are certified with IEEE 1547 and 1741, which is what you need to put in the microgrid. So there's the first level of distinction, right? We're going to talk about that. This is probably the most misunderstood part, why grounded delta transformer. And also the last thing is blackout grounding transformer. So we're going to go through those just to see essentially what we're doing, right? So this is Simulink 100 kW PV farm model, right? And with this particular module, you have a PV system on the right side, you have load on the left side, and you have a utility grid. If you do these simulations, right, you are going to see when you open the PCC on this particular model, you are going to see that you do have a voltage and that you do have a current, which means based on this particular design, the only thing you have in there is PV system as a distributed energy resource. Now, when you do things in the field, it's a little bit different because field devices have to be certified to IEEE 1547 and UL 1741. So what you see over here, essentially, what happens to the PV system when the PCC opens, right? You can see that current goes down to zero at the zero crossing, and you can see the voltage actually goes up, and then everything goes down to zero, right? Which means that within the microgrid that you're trying to put in, PV system on its own cannot sustain the microgrid, right? Again, it has to have IEEE 1547 and UL 1741 certification. If they don't have those certification, your models can produce what I just showed you about, right? So essentially what happens over here is that as your voltage goes down, the inverter detects the under voltage, and then the under voltage, when you open PCC, the inverter detects under voltage, and it tries to overcompensate. So it pushes the reactive power so that the voltage goes above. The 59 is the setting for the over voltage, and after 160 milliseconds, it trips. What you see over here is something that I actually had to add to the controls in order to make this thing behave as what we have inside the microgrid. So if you want to build a microgrid with PV systems only, there's no source of voltage and frequency if you don't have something else within the PV. Again, has to be 1547, UL 1741 and IEEE 1547 certified, right? So PV system on its own within the real microgrid installed in the field cannot hold the frequency. You do have some systems that PV can actually, supply the power to a light bulb or something like that. And I know research is moving towards there, but this is current field implementation. And a lot of times when we simulate transitions, we actually turn off the battery just to show everybody what happens when we only have PV system, right? Now, this is probably the most challenging part of the design, and a lot of PhD theses that I have reviewed and a lot of stuff that I have reviewed has a particular configuration with the transformer, and that thing can actually cause all kinds of challenges on the feeder that we're going to talk about. So what I have done over here is I've taken just a typical feeder, right, that has substation, and I have introduced the fault that's line to ground fault somewhere in the middle. And when I simulated the fault at the head of the feeder, what I've noticed over there is that it's 1633 amps fault that is seen. And, you have positive, negative, zero sequence current, so they're all the same for the line to ground current, right? And then what I have done, I have added the PV system at the end, and I have tied it through the transformer. Typically, PV systems have transformers on the AC side. Somewhere I have seen them as low as 315 volts. I have seen them as high as 480 volts. So the transformer that you see on the right side that's in green is Y grounded delta. This is probably, for some reason, the most common configuration that you can see in a lot of papers and simulations. And I'm going to show you why is that not preferred way to do things, especially when you tie it to the distribution feeder, right? So we tied the PV inverter through the Y grounded delta transformer, and you can clearly see as the DER size increases, the fault current seen by the substation relay reduces with the increased DER rating. So that means the higher the PV, the fault current magnitude that's going to be seen by the relay in the substation is going to be lower. This is for Y grounded delta transformer at the PV site or any DR site, right? So essentially what happens is that Y grounded delta transformer becomes a source of zero sequence current. So now the fault current that's seen by neutral CT, which is literally between the ground and neutral of that Y grounded delta transformer tied to the PV increases, right? And why is that so? Well, if you see this particular screen over here, pretty much simpler presentation what we have a fault current somewhere in the middle, and with Y grounded delta transformer, that now becomes source of zero sequence current. So the fault current that should go all the way to the left over the substation splits now. And that is not good because the relay settings in this case are desensitized. So what that means is that you will not be able to see fault for some particular size of the PV. And I have ran the analysis, and that says for about 2 megawatt size of PV on this particular feeder that I simulated, which is, generic feeder, we would not be able to see that stuff without typical settings. So our typical settings are, 900 for phase and, typical 600 for ground, right? So from that standpoint, you can clearly see that there is there's no reason to put Y grounded delta transformer unless something else is done to the protection and control settings, right? So what do you do now? Essentially, you have to change that particular transformer to the Y grounded Y transformer. And when you change it to the Y grounded Y transformer, the fault current seen by the substation relay does not change, right? Which is one major lesson learned. Also, if you take a look at arc flash analysis, it is probably 4 to 5 times higher than the incident energy released at a particular site is 4 to 5 times higher than with Y grounded Y transformer. So anytime when you design this stuff, just make sure you understand if you put Y grounded delta transformer, what is the impact on your settings, right? And I have seen a lot of designs with this Y grounded delta transformer because it requires an understanding of protection and control. And also, this also has major effect on the over voltages and everything that happens during the faults, right? So that's the first thing. Second thing, grounding transformer, right? So now when you have Y grounded Y transformer configuration, and if you have distributed energy resources, that means Y side is not grounded, and that is tied to your PV, to your battery, anything that is inverter based. Now we have a problem from the protection and control standpoint because when you have that particular configuration, there's no grounded source, right? But when you have synchronous generators, that thing is grounded, right? So that carries all around. If you have a transmission system, transmission system is delta, generation sources like synchronous generators, they're grounded. So outside the generation source, you have Y grounded delta transformer that is in the switching station. Then transmission is all the way delta, and then when you go to the distribution side, you have delta Y grounded transformer. So that Y grounded side of that transformer provides the ground for the circuit, right? But now inside the microgrid, if you have PV battery or something like that, right, and you have Y grounded floating Y, which is not what you must have because of the desensitization of the settings, now you need a grounding transformer because there is no solid ground reference. And if you ever try to do a lot of things, you're not going to be able to, right? So Y grounded transformer is really simple transformer. This is 500 kVA transformer that we have put in. It is Y grounded delta. We can see you can also put a zigzag transformer. And what you do is you put this neutral CT right there between the neutral and the ground, because that right there becomes the main source for pickup of the line to ground and line to ground faults within the microgrid, right? And then you have a relay over there. So what you do is you tie the relay, the neutral CT over to the relay, and then you have to do analysis to see, what kind of settings do we need. So the main purpose for the grounding transformer is actually threefold, right? You have to have a solid ground reference on 1247 kV side, right? Because PV system and battery, they are ungrounded, right? Second of all, to detect the faults, with this grounding transformer, you can detect about 95% of the faults. Why? Because line to ground and line to ground faults are the faults that you can detect with this stuff. You cannot detect line to line and 3 line to ground faults, right? And also, a lot of stuff that you probably do not see during the simulation. This is probably the most critical part. You might not be able to see that you cannot resynchronize to the grid without this grounding transformer. Because if you have Y grounded floating Y transformers, essentially what happens is that there is no grounding reference in the 1247, so your relay on the PCC, it can see reliably the grid side, but it does not see at all microgrid side, and you will see a lot of fluctuations. So that's the critical thing. Grounding transformer must be installed within the microgrid when you have distributed energy resources that have wide grounded floating by. So if you had a generator, you don't need it, right? But if you have battery plus PV, or if you have battery plus PV plus generator at any point in time, battery plus PV are the only resources within the microgrid, you must add this stuff, right? So the grounding transformer is disconnected when it's connected to the grid for the same reason that I showed you before, because it would have effect on the line to ground faults regarding if you have a DR or not. And it's connected to the grid. It's connected to the island when we go into the island mode, right? So how do you do that? Pretty much in your microgrid controller, you just put in when PCC is closed, this is open, or the way 3 or whatever you use to energize this transformer is open. The moment that you go into island, you open the PCC, then you close the grounding transformer, right? Now, when you go back to the grid, you actually have to hold this grounding transformer closed until you resync back up to the grid and until you close your PCC, right? And then you open it up. That's probably about 28 milliseconds after you close your PCC, you actually open this stuff. The reason why is if you open this grounding transformer before you close the PCC, your PCC 25 settings, which is sync check settings, they won't be able to see the right stuff because you have removed the source of grounding. So grounding transformer is probably one of the most complicated things to design of the microgrid. This is my personal experience. I can tell you I have designed a lot of things within the microgrid over here. So what happens essentially over here is the grounding transformer that you have over here will have to be designed, right? So you have two construction types. It's wide grounded delta or zigzag. It's a personal preference or engineering preference. The reason why I picked wide grounded delta transformer is because we already had it on the standard. You can pick zigzag. On an average, it's about 1/√3 size-wise less. But it's up to the engineer to pick one, right?
Hello?
Hello?
Hey, Alex, we couldn't hear you, but I think the mic is back now.
Okay. Do I have to go back on something, or?
No, I think it was just a brief moment, so I think we're good. Yeah.
Okay. So then you have a choice of primary and secondary voltage, right? 1247 kV wide grounded in this case because it's driven by the primary voltage is tying into. Secondary can more or less be anything. I have picked 480 volt delta. You can pick anything else that you want to. It's, again, an engineer's preference. But note that this grounding transformer does not have any load. So the secondary part of this grounding transformer is not connected to anything, right? Third one is impedance. Okay, so impedance can be designed a couple of different ways. IEEE 142 or IEEE 1547.8, which is more applicable to this application, which is pretty much the way that I have done it, right? One thing that you do have to understand for impedance is that X/R ratios of the transformer has to be greater than 4 to provide for solid grounding. I'm going to show you later on why this becomes a little bit more challenging. And if you ever, take a look at different transformers, you can see that probably over 400 kVA, you probably get that X/R ratio over 4. Particular transformer in our case is actually 500 kVA, X/R ratio is 5.09. This is really important because when you have line to ground fault on the system inside the island mode, your phase-to-phase voltage on the two unfaulted phases prior to the fault, if you multiply that by 0.8, that has to be greater than those same phase-to-ground faults after the fault. So this grounding transformer is probably the most challenging part, like I was telling you, right? When you have a islanding, you're going to have some kind of level of imbalance. So you have to design it with the steady state circulating current maximum level. That is a function of the typical imbalance. Now you have to understand that when you have motors inside your microgrid, you got to make sure that your imbalance is no more than 15% because some of those relays that you have are probably set at 15% imbalance. Also, battery energy storage system on its own, you can probably see that if they're set on the imbalance, which is a 46 setting, you're going to see that that's set at 0.8. So maximum level of zero sequence current is pretty much current that's flowing between Y ground and neutral. It's going through that neutral CT. The most critical design is neutral current fault withstand rating, right? What happens when you have a fault? And like I said, during the faults, it's line to ground and line to ground faults that you have to simulate, that you have to see what happens during those simulations. And also, there's a good paper by Michael Rupp that was presented at the WPRT conference in 2016 that talks about how to design the transformer, grounding transformer. But there are a couple of things that you have to think about. You have design that's empirical plus simulations. Then you have to simulate line to ground and line to ground faults. And also you have to test something somewhere in the yard or in the system where you have it. And to be honest with you, I have seen differences between design versus simulations versus actual stuff, right? So everything has to be designed with what you see literally in the field. And sometimes we need to fine-tune some of our approach or some of the design parameters in order to get to this stuff, right? And the last but not least is the KVA rating, right? So here's the key thing. This is the last thing that you worry about is the KVA rating because it has no load, right? And for solid grounding, your X over R ratio should be greater than 4. So the higher KVA ratings have higher ratios. So I can tell you 500 KVA transformers, this is from our 15-year experience, they have a X over R ratio greater than 5. So in addition to doing analysis that you need to do, you have to understand how does X over R ratio affect your fault currents. Because what you're going to see, if you don't have the proper X over R ratio, you are going to reduce the available fault current. And over here, as you can probably know, DRs, they already have very low currents. So you definitely want to have a solidly grounded system. However, the biggest challenge is how do you manage the inrush current so that the battery energy storage system can actually keep the microgrid alive during the transition, right? And we're going to talk about it later because this is probably the most challenging part. All right. Third section is seamless islanding. So our particular system over here at Mount Holly has a seamless islanding. So islanding can be either intentional when you go to the island as a function of some kind of operating parameter, or unintentional when you have a fault. And seamless islanding has to work for both, but you also have to make sure that you don't trip for some transients or some temporary faults on the system. So we have done islanding 3 ways. First of all, we wire 52A switch, which is the status switch of the PCC, directly to the battery controller. Why? Because the battery is the main source of voltage and frequency from the inverter-based distributed energy resources. Also, you can do that with the microturbine, but microturbine is slightly different from the implementation standpoint. So our AC coupled battery is the main source of voltage and frequency when we go into the island. So as you wire 52A switch, you have to wire that and transmit that real fast. So you know that 50A switch of the PCC, which is the recloser, you're looking at about 4 to 6 cycles. And when PCC opens, right, voltage and frequency changes happen much faster than the status of this switch. So we have seen that it takes about 4 to 6 cycles to open the recloser. And then we using, at this particular place, we have used serial over fiber. It's a mirror bit. It takes about 2 milliseconds to get to the, between the PCC and the battery, and then time to process. So this is probably the slowest way to do the stuff. This is something that we have done in 2014 and 2015. Then the number 2, what we did was we let the battery, that was our second option, we'll let battery inverter to detect the islanding based on the 27, 59, and 81 settings, which is under voltage, under frequency, over voltage, over frequency, and 27 is under voltage, 59 is the over voltage, and 81 is under frequency or over frequency, right? Without direct 52A status. The reason why we wanted to do that stuff is because if you ever build a microgrid, you might not have everything aggregated within your system. So essentially, we wanted to see, is that doable, right? And then the third way is when we actually have direct 52A status. I know there are some questions, are there no detection to zones or whatnot? I'm going to show you how our system works.
I'm going to show you results from the field. So we do actually have zero. We actually have zero non-detection zones, and you'll see why and how, right? Okay. So remember, I mentioned to you, this is simulation, right? This is what happens when you do seamless islanding. And as you can see, there are large voltage excursions. This is simulation, right? So you can see our regular voltage is about, 7,200 volts. That's 1 per unit. That's 120 volts on the, 120 volts. But you can see that we have these voltage dips or voltage sags that go all the way down to even less than 50%. So the question is, why does that happen, right? Transition is seamless, right? But remember what I mentioned to you is that you have to close the grounding transformer because the grounding transformer now provides your grounding, solid grounding. So what happens here essentially is that you have huge inrush in the transformer. You're probably familiar that depending on the size of the transformer, you can have inrush between 7 per unit up to 30 per unit, right? And the lower the size of the transformer, the higher inrush per unit is, right? So 25 kVA transformer can have a per unit inrush current to about 30 or something like that, right? If you have some bigger transformers, they can be 7 to 8 per unit, et cetera. So what happens in there, so remember, we have 100 kVA PV. We have battery, which is AC coupled. It's 650 kVA, right? And we have 500 kVA grounding transformer. So battery that is rated for 650 kVA, which provides voltage and frequency source, supposed to support inrush current into the 500 kVA transformer. Well, if this transformer has 7 or 8, per unit, then essentially how do we actually do this stuff, right? So I'm going to show you. I'm sure that a lot of you are familiar with the C37.118 single phase of data, right? What you have seen over here is simulation, right? What you see over here is just a part that shows the actual response from the field voltage sags. This is 27, right? Now, mind you, this is not to detect the islanding. We have detected islanding. We have gone into the islanding mode. This is strictly from the energization of the transformer. You can see 27P1P, the red line, is our first level of under voltage pickup. And then 27P2P is the second level. So you can see that these are the typical settings within the relays that would actually now have to understand, is this the transient or is this the actual fault, right? So what happens? Well, this is what happens, right? This is just one of those, and there are many of those. And depending on where you switch and how you switch three-phase, I have a section later on to talk about it, you can actually have this voltage sag really, really small or really, really large. So this is just one of those. This is what happens in the grounding transformer when you actually try to energize it, right? So the top line shows all three phases, IA, IB, and IC, right? The second one shows the voltages, and the bottom shows the inrush current into the grounding transformer that is between the neutral and ground. So why is there a voltage sag? There's a voltage sag because of the huge inrush current. There's a huge reactive power requirement to energize the transformer. It doesn't matter where this transformer is. It can be unloaded, loaded, whatever it is. It can be 7 to 10 times per unit for larger transformers, or you can have up to 30 for much smaller, right? So you can see over here in the second one, you can see voltage sag that actually goes below our 27.4P, or these are our settings right here that you see. So if you see, we have 0.88, and then we have also 0.5, and we also have 0.1 setting. So during the inrush, our settings would actually trip this. So you have to do protection and control in the proper way to avoid that stuff. Okay, so now look what happens to the frequency, right? Frequency response, our settings are 50.5 and 59.3, right, at 5 cycles. And during the transition, this is what happens. So let me just tell you what happens essentially during the transition. Transition, from the moment that we initiate islanding till the moment that the islanding is over, is 128 milliseconds. Our battery energy storage system has an inverter that operates in VSI PQ mode when it's connected to the grid. Even though you can operate CSI PQ mode, This one operates in VSI PQ mode. So it actually has to switch 3 operating modes within 128 milliseconds, right? This is what happens essentially during the operation of the microgrid with respect to the frequency settings. They go outside the normal range. So now you have to understand what happens with protection and control settings during this transition, right? So let me just tell you exactly what happens and how did we accomplish this transition, right? This is the basic stuff. There's a whole lot more behind it, but this is just the basic, right? If we go intentional island, right, we tell our microcontroller when we go to the island. That is done so that the microcontroller can tell the PCC relay to trip the PCC. Battery operates in VSI PQ mode. The moment we go to the islanding, we have something that is called 85 RIO scheme, right? 85 is the one of those schemes, just like 27, 59, 81. So this one's called 85, right? It requires DIDO, and I told you the communication is the fastest one using mirror bits, serial and fiber. So battery has to switch from VSI PQ mode to the VSI VF mode, or what probably everybody else knows is a Duke mode. And then what happens is that we have to trip the islanding switch. There's about 4 to 6 cycles, depending on what kind of recloser breaker you use. There's about 4 to 6 cycles time that it takes to break the arc and everything else. At that time, we actually, when we open, we send the confirmation to the battery inverter that we are open. Essentially what happens is that the battery has to switch from the VSI VF mode to the VSI ISO mode. VSI ISO mode is the islanding mode. You set the voltage at 1 per unit and you set frequency at 60 hertz. VSI VF mode is different, that you just give it a range. So for the VSI VF mode, our frequency is plus minus 1 hertz from the set point, and voltage is plus minus 5%. And once when we open, we have to close the grounding transformer. Remember, if you don't close the grounding transformer, you do not have proper protection. So you have to account for that. What happens if this fails, right? So this is the scheme that we use to island, right? If you have a grid disturbance, everything is the same except either our battery inverter or the PCC relay. They sense 27, 59, and 81. Now, there's a whole lot more to it. I got later on a couple of extra pieces that we sense, right? But pretty much the same. So if the battery senses first, it will send the information over to the PCC relay to trip. It's going to go through the same procedure. If the PCC relay senses first, it's going to tell the battery the same way, right? Okay, so let me show you. Let's see if we can play this video. Here's how islanding works. I just have to touch one point over there to open the islanding switch, and you're going to see wave 1 go from red to green, and then we're going to close the grounding transformer over there, wave 3 on the top. And that's pretty much it. And I can play it again so you can see. You can pay attention to the lights and everything else because this is inside the building. I'm sorry. This is inside the building, and you're not going to notice anything. You're not going to notice any light blink, nothing, right? Now, the only time that you will notice something is when we energize the grounding transformer. If there's a large sag, your motor is going to notice, right? But we have a section that talks about how do we do that stuff, right? So this is literally seamless islanding, 128 milliseconds, right? For those of you who want to know more about how it's done, their PCC is our point of common coupling on the left side. These are all the different settings that we have, 25, 27, 50, these are typical settings. 85 RIO scheme, right? So if you ever see the battery on the right side, battery has PLC and PCS, right? PLC is battery's kind of connection to the world. It talks to the microcontroller. It talks to the battery itself, BMS, etc. Now, PCS is power conditioning system. This is the part that actually switches the operating modes. And typically, every PLC and PCS, they have communication. Typically, it's Ethernet, but it uses usually proprietary protocol. So what we have done over here is we have added this DIDO, which is nothing but digital input, digital output block, and we have certain number of inputs and certain number of outputs. And using mirror bits, which is, like I said, it's about 2 millisecond delay between PCC relay and DIDO, right? Using these mirror bits, we can actually close some of these outputs and some of these digital inputs. Those are the inputs from the PCS and PLC. So essentially what we do is, if you see this output 306, That is the output that we close when PCC sensing the islanding condition to tell the PCS to go to the island, and then PCS does the switching, right? We also tell island command on the output 302 on the top to the inverter PLC, and the reason why we do that stuff, if inverter PLC does not issue a command to the PCS, because that's how typically it's always done, then we need to tell the PLC that we have issued command on our own, right? So that's the reason why we have the same stuff on top and the bottom. There are a couple other things. IEEE 1547 outside limits on the bottom on PCS. Essentially, that means that the battery can actually detect islanding in some cases before PCC, so that's why that is done. So essentially, if PCS does that, essentially what happens is that the PCC relay knows that it needs to open, and a few other things. But essentially, this is how we accomplish seamless islanding. There's a lot over here behind it, but this is just kind of the basic idea in between. Okay. So somebody asked, how fast is this scheme, right? And somebody asked about non-detection zones, right? Well, here's what I can tell you. The blue line and the green line that you see over there, that for PL over PG equals 1.0, which means that the loading is equal to the generation at that particular stuff. They are based on the 2751, 2759, and 81 settings. This is from a book and from a paper that was written. If you search, it's a SEL book that was published probably last year, and they have these curves over there, right? If you see our scheme that I showed you over there, right, you can see 3 lines, right? Actually, you can see 4 lines, but 3 lines that show the response. The red line that you can see over there, that is the line that shows the detecting time for the island, which is on the left side. The detection time, if it was detected by the battery inverter PLC. The yellow line underneath is essentially the line that shows what would happen if we had 81 settings, right? Which majority of the time on our system is the 81 setting that detects the islanding. And then the last but not least, on the bottom one that you can see, the fastest one, is something that is called DF over DT, which is the rate of change of frequency, which is much faster than 81, right? And I can just tell you, we were doing this test numerous times for different PL over PG ratios. You can see they go from 0.0 to 2.0. And with 85 RIO scheme that we have implemented, I showed you, you can actually detect this this islanding with all 3 of these, right? Just to let you know, I have a bunch of slides over here. You can probably see the settings for each one of those. But the stuff that we have over here has been tested several times. We tested in the different temperature conditions, when it's really hot, when it's really cold, and these are the results that we have received. Now I do have to tell you, sometimes you can see the numbers over here on the left. These numbers they were actually tested with us actually opening point of interconnection. So I showed you we have point of interconnection, which is recloser upstream. They can also simulate, breaker or something like that. We would actually open that stuff. However, if you ever try to test that stuff, if your scheme is too fast, which ours was, if we try to detect that on the change of 52A switch, that thing would never have anything. And the reason why we have anything, because the system changes much faster than the switch opens. So these numbers right here on the left side, they're actually much faster in real life, but we actually had to initiate the event recording on our pushing the button on the front of the relay to go open, which means that there's still, some time after that. So even at these speeds, it's really fast, but a real life it's actually even faster, right? So 2 things: scheme can detect islanding for PL over PG, right? You can clearly see there's no non-detection zones. And second of all, I know if you see on this particular screen that there is a response time between 0.0 and 0.2 PL over PG, that means that we have a whole lot of generation, not very much load. we have tripped every single time. We have tested this probably about 30 times, and we have proved that there's something called load rejection over voltage. When you have a whole lot of generation and when you do not have a lot of load, essentially in this case means you have somewhere close to infinite generation, battery inverter is going to trip on its own. Why? Because it does not have enough time to change its voltage and frequency based on even in its settings. So just to give you an example, settings can be 1.1 per unit. They can be like 132 and 144 volts. Voltage is measured, they were like 145 to about 164 range. So there's no way to get out of this seamless transition during P generation much greater than PL. You see 0.0, 0.2. 0.2 is the kind of smallest ratio that we managed to still seamlessly island, but anything below we have tripped. And for PL over PG equal 1, we have tested this probably about 15 or 20 times for PL equal PG, and every single time we managed to do that stuff. Okay, probably the most challenging part, transformer inrush current mitigation, right? What are we doing? Okay, so you saw that what happens during the voltage, during the energization of the transformer, you have huge inrush current into the transformer. If you close everything three-phase, right? And that right there is a function of residual magnetism of the transformer and where you actually switch. So what I have done is I went and simulated about 9 different things what we can do, because remember, you have 650 kVA battery and you have 500 kVA transformer. So that means now you're going to have a whole lot of inrush current in there. So how does your 650 kVA battery can potentially support, something that's 7, 8, 10 times 500 kVA, right? So this is typical. This is what happens, right? The second thing that I was simulating is, what if we have 2 circuit breakers, and what if we put pre-insertion resistors, right? What kind of results do we get if we use that, right? The goal was try to find 2 or 3 things that might work and then implement that. The third one is, what do we do if we put neutral resistor, right? This is something that happens all the time, but this is something that you don't want to do simply because when you have islanding condition, it will help with inrush current, but it is not going to help when you have a fault, because this will actually reduce the amount of available fault, this neutral resistor. Also, if you ever have a delta Y grounded transformer and try to do the inrush into delta side, you can't do it because there's no place to put this neutral resistor in, right? Another piece that we try to put a smaller transformer, right? So what you would do is you would pre-energize the transformer going through the smaller transformer. Some studies have shown that this smaller transformer has to be about 0.5% to 1% of the big transformer. So in this case, that means this will have to be in range of 5 kVA. So the problem is, how do you build 5 kVA transformers at 1247 to 1247? It is physically impossible. So this wasn't the case, right? So we tried to do the same, trying to add the resistor or reactor, because as you know, as you add resistor or reactor to the circuit, you reduce the current going in. But the 5 kVA transformer is what kind of got us out of that option. So this is one of the options that we have done. We actually put 2 transformers back to back, right? So what you do normally is you go up, you close the circuit breaker 1, that energizes 2 of these transformers that you close the circuit breaker 2, and then that actually energizes the big transformer through the 75 kVA transformer. And once when that is energized, you close the main circuit breaker, and then you trip these 2 circuit breakers 1 and 2. Unfortunately, the lowest transformer that I could find that is built is 75 kVA. So we go from 1247 to 277, 480, and then we just flip-flop. So 75 kVA is the limiting factor, so that means that particular current would have to be higher. Plus, if you ever install this, there's significant cost because all of this stuff is high voltage stuff. Another piece that we have over there is, what if we change this particular circuit breaker that's 3-phase to a single-phase, and then try to operate based on the point-of-weight switching, because that can reduce current. That is true, but also, I did another analysis, and that analysis showed that depending on your residual magnetism, even if you switch at 90 degrees, which is what you would typically want to do when you're switching on a point of wave, essentially what happens is that you can end up switching with the higher inrush current, right? Now, just want to let you know, when you switch single phase, remember, between neutral and ground, there's a CT. When you switch single phase, you are going to have full current going through that neutral CT, which would cause it to trip, right? So when you do your protection and control, you got to make sure that you don't switch for that, right? So there's something that's called torque control, right? You have to torque control for this condition. If you intentionally try to energize the transformer, that you actually have to torque control those settings, right? For anything other than the true fault, etc., this neutral CT must not trip, right? So that's part of the security scheme. Every time when you do some kind of a scheme or testing on a system, you got to do reliability to make sure that stuff trips when it's supposed to trip. But then you have to introduce all of these temporary faults and all the other stuff and make sure you don't trip on transients. And then the last one over here that we have tried with, what's kind of currently available on the market with respect to the controllers is using residual magnetism, right? And we have actually implemented a couple of those, right? And this is essentially the implementation that we currently have in order to reduce the inrush current into grounding transformer, right? We have, look at the B3, that's our kind of way 3, right? And if you look at the straight line that has a controller and 25 relay, that is the relay that actually energizes grounding transformer based on the residual magnetism, right? We have 2 different controllers that we're currently testing. Then we have a way on the top side, you have CUC breakers B1 and B2, that's kind of going through the transformer on the lower side. And then on the bottom, this is something that I came up with where we essentially use the pre-magnetization on the lower side, right? So there are 3 ways that we're currently testing, trying to see. I have simulated all of those. They all are giving us some results. So we got to run through about a year of testing to see which one is the best and what are the pros and cons of each one of those, right? Because remember, it depends on number 1, temperature, and number 2, when was the last time when you actually operated a particular device? Because if the device is sitting there through about 3 or 4 seasons, it's not going to have the same operation as if you have operated, yesterday. Okay. So now, probably one of the most challenging parts, how does the microgrid operate, right? Well, we have several modes, right? We have manual mode, we have net zero mode, which means that we try to keep KW at 0 at PCC, and we have auto mode on the right side. So most of the time we operate in auto mode, right? And on using this mode, we actually stay anywhere between 21, 22, 23 hours off the grid, right? We ran it in this particular mode over 4 months without any user input, and then we actually had to stop it because we were adding generator and microturbine, right? So this particular system works, right? So net zero mode, you can see it's a blue line over here. The reason why it's never exactly 0 is because some of these devices that you communicate, they're DMP3, some of these devices, they're Modbus. So by the time you get to it, they calculate it's going to be somewhere close to 0. It's never going to be 0. Second of all, you do have to understand CTs that are typically the 500 to 1 or 1,000 to 1. Over here, they're 500 to 1. They have inaccuracy at the low currents. That's about, 5 to 6% on the magnitude. It's somewhere about 6 to 7 or 6 to 8% on the angle, right? Now, if you get out of net zero mode, if your battery is connected to the grid, you have to actually operate battery in state of charge management mode, right? Because battery is going to trickle charge if you don't operate it this way. So that's why we have, higher current. Okay, so how does this mode operate? I have shown you equations. This is what happens in real life. Look at the left side. That shows power per unit. That's your y-axis on the left. Y-axis on the right, that's the battery state of charge. And then x-axis is time, right? So we keep our battery between 90 and 70%. So if you take a look at on the left side, you can see battery state of charge, right? In the middle, you can see different kind of powers. The green power that you see, power green, that's from a PV system. Purple is battery. Red is our load. And orange is a load within the building. Red is the load that we can actually control ourselves, right? So essentially, as long as the green stuff, as long as the PV is greater than our load, we actually charge the battery. Once when battery reaches 90%, which is right there in the middle, on the left side on the top where it says battery max SOC, right, we turn on the load bank. We can actually curtail the PV, but in this case we don't do it because we have enough load that we can turn it on, right? So we turn on the load bank at 125 kW. And at that time, you can see how the battery starts discharging. When the battery hits 70%, we turn off that load bank. PV is greater, which is green stuff, is greater than our orange, which is the building load. So we start charging the battery. So we go battery up and down until somewhere around 7 p.m. You can see how green goes to 0, which means there is no PV, right? At that time, battery becomes the sole source. So you can see how battery state of charge starts going from 80% and gets all the way down to 10%. That's pretty much in the middle of the night. I showed you how we do the island. I'm going to show you later on how we do resync. So when we reach 10%, the system automatically resyncs. We charge the battery from the grid. We get to about 90%. You can see that takes about an hour and a half, depending on, the demand. And then, again, battery is the main source. So somewhere around 3 or 4 o'clock in the morning, battery, again, disconnects automatically from the grid, becomes, again, the main source of voltage and frequency, main power source. So it goes down, right? So when it gets down to about 60%, you can see around 7 or 8 a.m., there's about 60% SOC. Green line, which is PV, becomes higher than the orange line, and then we start charging the battery, right? The addition of the generator and the addition of 2 microturbines can actually enable us not to actually connect to the grid at all, right? So when we get down to 10% or whatever that is, we can actually turn on the generator that we have just recently commissioned probably about 2 weeks ago. And then once when we commission the microturbine, we can also turn on the microturbine. So we got more generation in this case than we need. The generator is actually a natural gas generator. If you ever deal with these generators, you know that natural gas generators, they have a little bit slower response than diesel generators. But both natural gas generator, both generator and the microturbine are natural gas. Also, we can actually we do have a load shedding scheme over here, but in this case, I haven't shown it. But there is a load shedding scheme. And what I told you a long time ago, I think on some of the first slides, you can see where's the inrush current. This is from S&C Electric Selection Guide for transformer primary fuses. You can see what is the per unit inrush current to different size transformers, right, as a function of time milliseconds. So probably one of the most challenging parts is that how do you energize the transformer? And in order to do that, you have to have these curves and you have to figure out how do you actually minimize the inrush, because most of the time I don't know if your generator is going to be running, And also you have to understand when you do the black start versus seamless islanding, which is in this case, there's a major design difference, right? Because when you do black start, you're going to follow one design methodology versus seamless islanding with respect to the size, right? So as you can see, when you try to do cold load pickup, it's much more challenging to pick it up, right? This is, again, different utilities that have shown what are their inrush currents, as a function of time when you have to do cold load pickup. And again, that's function of, are you doing cold load pickup 5 seconds, 2 minutes, or an hour after you went, after your main grid was lost, right? So let me just tell you what I did was I did just generic implementation for generic microgrid if you have 100 kVA PV and if you have 150 kVA battery. And I tried to see what does it take to do the cold load pickup. And I did Monte Carlo analysis, and you can see this is just one slot, right? And you can see I would fail every single time, right? Why? Because everything that you can see in terms of inrush is higher than the battery energy storage system rating, right? PV cannot help you a whole lot during the cold load pickup, right? So 50% of all of the inrush currents, and I've done about 10,000 simulations, they're about 400 kVA, right? Again, my grounding transformer in this case was only 125 kVA, right? So that means that when you design the battery, if you want to do cold load pickup, you have to do a whole lot more than as if you're just doing seamless islanding. Because when you do seamless islanding, the only thing that you have to worry about is the inrush current to the grounding transformer. When you do cold load pickup with battery plus PV, then you essentially have to worry about every single transformer that's in your system, right? And you probably know the size of the transformer can be 3-4 times the maximum load. So now you have that thing going against you, right? So essentially, when you do microgrid for seamless transition, you can do the peak microgrid loading, you can also implement volt-var control if you have it, right? If you do cold load pickup, Then you have to size everything for your transformer kVA/MVA rating. And then you have to look at your historical cold load pickup quantities. Unless you start implementing different things on your feeder to sectionalize the feeder and all of your transformers so that you're not picking up everything, you're just picking up sections, et cetera, right? You can also use your maybe line reclosers, but that requires you to have some different communication schemes for that stuff, right? So there are a lot of requirements. This is me just telling you, basic stuff on the seamless transition versus cold load pickup, right? Now, seamless grid resynchronization. Remember, if you have Y grounded Y transformers on your DERs, you need that grounding transformer. Without the grounding transformer, you won't be able to synchronize because your PCC relay is going to block it, right? So the way we do this, we essentially initiate grid synchronization sequence. Our microcontroller enables the grid auto connect, which means that we want to make sure we have a healthy voltage on the feeder, that it's not just coming in and out, right? When the PCC relay said, yeah, I have stable voltage for 5 minutes, we start the grid sync procedure. So that's done through that scheme where we tell battery inverter that we need to go to the back to the grid. So the battery is going to change from VSI ISO to the VSI VF mode. And when the battery syncs up, it's going to tell the PCC relay that the grid sync has completed. PCC relay is going to check its own 25 settings. If everything is fine, it's going to close the idling switch. And we're going to tell another relay to open the grounding transformer, right? And then when that thing happens, we're going to tell that PCC has closed, that we didn't have breaker failure or anything like that. So that's kind of simplified version of what happens, right? And the battery inverter is going to stop sync procedure because it's going to go back to the VSI PQ mode, right? So if you ever wanted to see how long does that take, you can take a look at this stuff. Sometimes it's anywhere between 2 and 6 or 2 and 8 seconds. If you look on the bottom left, you're going to see 2 green and 1 red. That's our delta V, delta F, and delta angle. So you can see right now that during the grid synchronization, battery is going to bring all of these 3 into green. And there's a 2-second update on this particular screen. So you're going to see grounding transformer is going to open actually in reality after the wave 1. So as you can see, there was no voltage dip. We didn't lose any lights, et cetera. So you can see that it is seamless. And for those of you who have seen or who are familiar with IEEE C37.18, here is grid idling, seamless idling, and seamless grid resynchronization as seen by the syncophasers, right? So just to show you what it is over here, on the top left side, you have frequency. Blue is grid, yellow is microgrid. They're on top of each other because PCC is closed, right? On the bottom left, you have voltages on both sides of the PCC. You can see that they're a little bit different, but right now the PCC is closed, so they should be on top of each other. But as you probably know, every time when you build PT, they have small inaccuracy, even though if you look at the numbers, they're all close to each other. On the bottom right, that's an angle difference between the grid and microgrid. And then on the bottom right, on the top side, the green line, that's a PCC status, which is 1. And on the bottom, there's some kind of, brown that says request to close. So essentially, I'm going to play this. I'm going to tell you what happens, right? So first, we are connected to the grid. And at one point, you're going to see the green line go down on the bottom right. That means PCC is open. And you're going to see voltage. There we go. Voltage and frequency jump, right? This is response during the 128 milliseconds, right? You are going to see voltages on the left. You're going to see on the right. You're going to see how angle within the grid and angle with microgrid is not. And now you can see on the bottom, we issued the request to go back to the grid, and you can see immediately after, because the angles were really, really close, they closed within probably half a second or so. Typically, it's about 2 to 6 seconds. This stuff. This is syncophaser data, right? So everything that you see over here, you have one sample per cycle, right? All right. So somebody asked, how fast is our scheme? What do we have, et cetera? And how does it work? So I showed you that we detect based on under voltage, under frequency, over voltage, over frequency. And then we have added 81R and also single phase based islanding scheme, right? So 81R is rate of change of frequency, right? So I told you already how to initiate the islanding. I told you how fast is the current scheme, right? Well, you can see the fastest scheme is actually the rate of change of frequency, that df over dt. So the question is, as I told you before, this is similar to before, right? So the question is, how do we do that, right? So in order to do that, we have tested numerous things, right? And what you can see over here is response as recorded by the relay for PL over PG equal 0.4. On the top, you have frequency. Then you have a voltage on phase A. Then you have the rate of change of frequency, and then you have essentially what happens on the feeder, right? So input 212 on the bottom is when we actually initiate the islanding by pressing the button to open the islanding switch, not islanding switch, but the POI, point of interconnection. What you can see over there is that the yellow line shows when TMB1B. TMB1B essentially in this case is the mirror bit from the battery, and you can see for this particular calculation or for this particular case, for different ratios for PL over PG and different type of load within the microgrid, this remote bit TMB1B, essentially that means that the battery inverter has detected the islanding, right? But you can see how the rate of change of frequency has changed during that time much faster, right? And that's DF, DT, PM. You can see on the left side that range. And I can tell you that we have tested different ranges. I have pictures over there so you can see pretty much where the set points are. This is just to show what happens during the islanding, and then how does DF or 81R, rate of change of frequency settings act, right? Here's the same thing for PL over PG equal 1.0, right? You can clearly see on the left side input 212. Again, that's our us pressing the button on POI to open the upstream recloser. 27P1P, that is essentially when would islanding be detected by the when would islanding be detected by the undervoltage. 81D2 is actually showing when was the islanding detected by the overvoltage, right? But then you can see clearly that DF over DT has changed a lot depending on where we are, right, in this whole scheme, right? So in order to show you a little bit better, I have actually zoomed one of these responses, right? So look at the top. That's our typical frequency. Somebody asked about frequency settings. It's 59.3 on the under frequency and 60.5 on the over frequency where we detect. So if you take a look on the top, you can clearly see the pink line. It's kind of showing when is 59.3 setting picking up, right? You can see that. That's your 81D1. We actually have time delay, which is about 5 cycles. So you can see on the bottom 81D1T when that thing times out. That's essentially when we would. That's essentially when we would actually go to the islanding mode, right? But if you take a look at the middle one, right, you can see that 81R, rate of change of frequency, reaches point of minus 2.5 hertz. And 2.5 hertz is something that I have found in literature that everybody's talking about as a setting. So I just wanted to use something as a frame of reference for this stuff. So you can clearly see that 81R goes below a negative 2.5 hertz almost immediately after the 81U or under frequency picks up, right? Now, that means that 81R scheme over here would be faster by close to 80 milliseconds. But remember, certain things happen on the feeder, and just because 81R detects, you can't just go over there and say, oh, I'm going to initiate islanding right now, because it might be one of those transients. So in order to increase the security of the scheme, this 81R setting has to have some kind of time delay. So we have taken time delay of 2 cycles to be enough so that we kind of take out all of the transitions that are actually resulting in some sort of a unwanted islanding, right, where it's just some kind of temporary fault or something like that, right? So you can clearly see on this one how much 81R is faster than 81U, right? So that means probably 3 cycles faster, right? So we have ran this again for every ratio PL over PG, right? I ran this with a set point of 2.5 hertz per second. Remember, as a function of PL over PG, excuse me, 81R is either going to go positive or negative. So it's essentially 2.5. So if it's less than minus 2.5 or greater than 2.5, right? So just to understand how this works, right? We have seen that our idling is the fastest when we have under frequency. It's much faster than the under voltage, right? So what happens is that this particular chart shows if you put 81R at minus 2.5, which is the green line, right? That's where you would essentially initiate idling minus 2 cycles. Now you can see the red line and the blue line. The red line shows when 81U, which is the under frequency, or 81O, depending on which side of the PLM or PGI, right? Are you less than 0.1, less than 1.0, or greater than 0.0, right? But that means red line means that when 81 setting picks up, and blue line means that when 81 setting picks up and times out after 5 cycles. So, for example, if we pick say 0.4 PL over PG 0.4, so essentially what happens is that 0.4 PL over PG. That means that for 2.5 hertz per second setting, you can see that 81R will change, and it will be 12.48 when 81U picks up, and it will reach 15.12 when 81U times out after 5 cycles. So essentially, you can actually even torque control this setting if you want to, right? Interestingly enough, you can over here see that for 1.0, they're kind of the smallest, the deviation between 2.5, which is kind of what is expected, right? So in this case, you can clearly see that if you have 2.5 hertz per second, it works, right? Now, everything that you see over here is essentially it's a function of a fault, but when you have 2.5 hertz, you got to make sure that you don't trip for something that's temporary, right? So in this case, you can just see the percentage improvement if you use 81R at 2.5 hertz setting. Everything that you see over here is tested in the field. Okay, this is not something that was simulated, and I'm not showing you simulation results. I'm showing you actual results from the field. Right, just like everything else, everything that I have shown you in this particular presentation is what we have measured in the field. But like I told you, just because you put 2.5 hertz and we have faults and everything we have calculated, that doesn't mean that that the simulation is done or that the testing is done. What you have to do is you have to account for security, right? You have to see what happens when majority of the things change within the microgrid. And when you have this transient analysis that you don't trip when you're not supposed to trip. So we have done these 5 cases, which are 5 critical cases in our stuff, just to make sure that we don't trip on 81R setting, right? And you can clearly see that for none of these cases we trip, right? So remember, every time when you do something, you have to do the fault analysis or reliability analysis, but you also have to do security analysis, right? Now, we wanted to improve this further, so we wanted to do synchrophasor-based idling detection, right? Synchrophasor-based idling detection, that means you have 2 relays at 2 locations that are tied through the fiber or some kind of network using synchrophasor data. So if you go over there and there's a standard, there are probably a bunch of papers. Essentially what happens is that on the source side of the breaker, you have relay that has GPS. You have communications to the microcontroller. On the load side of the PCC, you have relay with GPS also connected to the microcontroller. And now the microcontroller has to use synchrophasor data to detect the islanding. Why? Because as breaker opens, the voltage starts deviating, the frequency starts deviating, the rate of change of frequency starts deviating. So from that standpoint, you can see that there is a way to detect it, right? So for those of you who might not have seen this before, this is essentially how we do the stuff, right, from the standpoint of testing. You can see this is our microgrid yard, right? You can see point of interconnection, right? So all of these tests we have done, all the testing was opening this POI. The source side of POI has PTs, right? They are tied to the relay with GPS. Now, we could have had this in the substation or anywhere else. It would have been more or less the same results, right? Just a longer fiber, but it's speed of light, so it should be the same, right? And then we have a PCC
over there with its own relays, PTs, and all of the GPS network control, etc. So what we did was essentially we ran the communications cable from the relay that is tied to the source side PTs of the POI over to the network switch where the other PCC relay is connected to, and we tied all that to the microcontroller. So once when we have that stuff, then we have to do the field settings, right? So field settings are based on two things, right? There's a voltage angle difference, which our set point was greater than 10 degrees. And then there's a slip frequency and acceleration, right? So for those of you who might not have seen this, slip frequency is the rate of change of voltage angle, right? And the acceleration is the rate of change of slip frequency. So you have this voltage angle difference set point, and then you have the screen on the right side. So as long as you're within the green, you know, that's a normal operating region, right? It doesn't mean that the voltage would not take you out, right, from the standpoint of islanding. But this is the single phase of base island. This is just the frequency section on the right side, right? So you write these equations, you implement it in the field yard, and essentially here's what happens, right? This here shows single phase of base islanding versus 81R, right? So remember, we have 81, we have 27, 1519, 81U, 81O. We have 81R. Now we have synchrophase base islanding, right? Synchrophase base islanding is the only sure thing that you know, probably if you read it, just about anything. That means that you can definitely detect for PL over PG equals 1, even though our field tests have shown that even for PL over PG equals 1, we can detect with our own local measurements. But you can clearly see over here that it takes a little bit longer, right? Now, I do have to tell you, everything that I have shown you in this presentation has been done over probably about a 2 to 3 year period of time. During the last 2 years, we have done close to 7,000 transitions between grid and microgrid, which is, I believe, significantly more than just about any microgrid in the world. And this testing that we have done, we have repeatedly done some of this testing. Some of the response times that you see here might be slower than what you have seen before. And the reason why, I can just tell you that the switchgear, the 4-way switchgear that we built, that we installed originally, that switchgear is built only for 2,000 operations, okay? So when you try to operate the switchgear 3 times past this, you know, operating life, certain things kind of get slowed down, et cetera. So this is probably something that you wouldn't see this slow, but, I mean, you can clearly see that we can still detect islanding based on both of these methods. And as expected, single phase of base islanding is the fastest one with PL over PG is equal to 1. But again, just note that this particular testing was done probably about 2 months ago. So after about 6,000, 7,000 operations, it's not the same response time as after about 1,000 or 2,000, right? So some of these times were not done at the same time as some of the stuff over there that you have seen, right? So you can clearly see the single phase of base islanding works. As expected, it's slower than, you know, 81R. Also, it's slower than 81U or 81O. But for PL over PG equals 1, that's sure way for you to actually detect it the fastest way, right? Now, everything that you have seen in the microgrid was done typically using DMP3 and Modbus protocol. And I have done design of all the protection and control and all the high voltage stuff. But we have also done a lot of wiring in the yard. So what we try to do is, can we actually use IEC 61850 and some kind of control techniques to actually protect this microgrid, right? Why? Because that simplifies wiring, that reduces the cost of implementation, et cetera, right? So I'm going to show you now how everything looks like, right? So this is the yard that we were talking about, right? So in order to do 61850, you probably know that you need communications, you need merging units in the field, and you need relays at the back. So every single piece that you see over here in terms of normal protection and control has its own associated merging unit that is operating in parallel, right? So the 4-way switchgear has 2 merging units protecting it, MU1 and 2. The grounding transformer has another merging unit, which is number 3. Transformer, we put differential protection, so merging units 5 and 6, they protect it. There's nothing on PV side. Generator has its own merging unit. And also, we're waiting for merging unit number 7 for 2 microturbines, right? So all the work that we have done was with respect to all the merging units and excluding merging unit 7, right?
So how does this look, right? So what you see over here essentially is the internal enclosure that protects four-way switchgear. You have traditional protection on the left, right, relay. Then on the bottom you have emerging unit 1 that's tied to the way 1 and way 2 of the four-way switchgear. And on the right side you have emerging unit 2. Now when you have merging unit, remember you have your CTs, your PTs, and your digital inputs, digital outputs, right? So these are merging units 1 and 2. On the left side, you can see merging unit 2, right? These are the CT and PT parts. So some merging units are built to take both CTs, PTs, inputs, as well as the digital inputs and digital outputs. Some of them, they have separated, right? In the middle, you see grounding transformer that has traditional protection and merging unit 3. On the right side, you see a generator. Again, everything has a traditional protection as well as the merging unit. We also have selector switch, so we can switch in between the two. You can also see on the left side, these are the fiber optic current sensor that we are testing. That itself has its own merging unit. We have some Rogowski coils on the low side of the transformer that actually have RJ45 as output. So these are the new CTs that we're testing. You can also see what is being built now for the microturbine, another merging unit, and traditional, again, we have selector switch. And then on the right side, so what we decided to do over here, we decided to put merging units for 4 different vendors, and also on the back side, we have relays from 4 different vendors. So if you take a look at everything with IC 61850 based on the standard, you can mix and match, right? So the idea was what we're going to do is we're going to do 5 phases of commissioning, right? Number 1, we're going to get one vendor just to read their own units, right? So each one of these 4 vendors should be able to read their own units. Then the next one, each one of these vendors should be able to read other vendors' merging units, right? And then we would implement settings, and then we would do the 85 RIO scheme to enable seamless sounding, and also load shedding transfer trip scheme would be number 5, right? So we managed to get to number 3 now. When you have 61850 protocol, essentially, as you probably know, you got 2 things, right? You got sample values, which are CTs and PTs, right? And you got your goose messages for status points, right? So everything in there in the 61850 is a function of your communication network. So you have to understand how to put this communication network to make sure that it works. All right. So these are the lessons learned, right? I can just tell you that originally we just wanted to put 2 merging units, but that thing has changed. So as we kept adding more and more stuff like generator and the differential protection and stuff, we changed. So our strategic design approach, and I think I have misspelled design, essentially was really not all that strategic because we kept changing and we kept expanding. So when you do this stuff, just make sure, just from our personal experience, just make sure that you identify your scope of work and then you do that stuff, right? Next of all, your system, your switch has to support PTP, which is IEEE 1588 protocol. Typically, majority of the switches, they are either NTP or something else. This one has to do PTP protocol, right? And the vendor interfaces. So why do we do 61850? As you probably know, when you do typical protection, you have to run a lot of copper wires from the yard over to the substation. That's a lot of copper, right? And also the biggest challenge is how do you make sure that those copper wires stay there? How do you make sure you don't have open CT circuit, et cetera? So in this case, what happens is that you put a merging unit right inside the breaker, transformer, wherever that is, and you don't run any copper wires. The only copper wires, everything that you run is to the merging unit. And then you run a fiber from that merging unit all the way over to the substation control house. And then what happens is that you take another relay over there, and that's when you convert those signals back to calculator, right? So that significantly reduces the amount of copper that you have to run, because some of those copper runs are over 1,000 feet, et cetera, because in particular substation, you can have, 10, 15, 20 breakers that are far away from the house, right? So in order to simplify design, you run these fiber cables. Well, fiber cables, they have different speed, right? So some of those are 100 megabits per second, and then some of those are 1 gigabit per second. And some of the vendors, they run only 1 fiber. Some of the vendors, they run 2 fibers. And then you have to see how your network is going to be, So you have to make sure that you understand what are the requirements from each vendor, because every vendor is different. And then because you have to tie everything to the fiber switch, you have to make sure that the interface speed matches whatever the speed is from the merging unit, right? And then when you have a fiber switch, I'm sure that everybody receives email, right? So this is kind of, you can equate this to your email, right? How many emails do you get per day that are, just a spam email and stuff? A lot, right? But there might be only certain number of emails that you want to, see. So when you get all these fiber runs, right, you are getting the sample values, which are currents and voltages, and you're getting goose messages, which is the statuses and controls, right? So when you get to the switch, the first thing you do, you partition, right? So you can take two switches or you can take one switch and partition, doesn't matter. You have to create two buses, right? One is a process bus, one is a station bus, right? So this is for your sample values and for your goose messaging, right? Well, if you create a bus for your sample values, right? And if you have, I don't know, say you have 30 sample values coming from the field, and you have about 4 or 5 relays in the back. Well, every relay doesn't need to hear everything, right? So that's equivalent of if you just put everything on one bus, then every relay is going to be hearing or seeing all of the data that it even doesn't need to see. Now, there's probably, I think, 6 or 7 megabytes per second of data, right? And I can tell you, if you put on our side over here, if you put a Wireshark on all of the sample values that are coming in 10 seconds, you're going to get a file that's about 400 megabytes, right? So that's a lot of time, right? So what you do, you want to do some filtering. It's called MAC address filtering or something like that, right? So you want to make sure that your relay in the backside only sees merging units that you need to see, not every single merging unit, right? That's called fiber switch partition, right? So we had the option to install 2 fiber network switches, one for process bus, one for station bus, again, either sample values or goose messages, or we could do one fiber network switch and have everything come into it, so we have VLAN 0, but this is not according to the standard, or we had one where we can do one fiber switch and we can separate process bus and station bus, which is what we did, right? So if you wanted to see how does this work okay, here we go. So this is essentially how this solution works, right? On the left side, on the bottom left, you have different merging units. And I have put which merging units actually have 100 M and which merging units have 100 gig, because remember, you have to size it with that. Merging unit number 5, I told you that all the merging units take PTP clock. Merging unit number 5, which is the merging unit number 5 is the PPS. So essentially, we do this stuff. We run it, and I'm going to show you essentially on the left side, you can see how the relay in the back office receives the data from different relays, from different merging units from different vendors. This is the relay from a different vendor doing the same stuff. On the right side, you can see IEC 61850 operation, and unfortunately the video won't play. So I think what I'm going to do is pretty much stop right here, because it seems like we're getting close to the end of the presentation, and I can see if there are any questions that I can answer.
Hey, Alex, thanks a lot. It was a great presentation. I enjoyed it personally. I'm pretty sure everyone else on the call had a great time listening to you and the great work you guys did at Duke. So with that being said, we're going to open the session for Q&A. And anyone who has questions, please feel free to type it on the chat window. I know that Venkateshwar already had a bunch of questions previously, and same with a few others on the call. So, hey, Venkatesh, if you're still on the call, please feel free to type in the questions, and anyone else, please go on. So Sagar has a question. Have you tried the operation of microgrid only in the presence of microturbine with the natural gas?
So the answer is we have not commissioned the microturbine yet. As you can see, it's missing the 480 volt switchgear, which would be here in about 3 weeks, I believe. We have operated with the with natural gas generator, and we have actually done seamless sounding and seamless grid reconnect with natural gas generator and PV. The moment we get this switchgear, I don't know if you noticed, but there's a lot of wiring involved with microturbines. This particular microturbine is 65 kV, so it's going to be operating like in current source mode, so to speak. 200 kilowatts or higher, they can actually do seamless islanding too. We have operated, like I said, with natural gas generator as the only distributed energy generator that has a natural gas as a source as of now.
Awesome, Sagar. That answers your question, right? Okay, so the next question we have is from Venkateshwar Reddy. The question is, as per LVRT scheme under voltage sag at grid side, MG microgrid supposed to support the grid, but islanding detection scheme trying to island based on set limits as per 1547.
Yeah, so you have to understand where you're located, right? You have 1547 that works, but let me tell you something. You cannot wait for IEEE 1547 to work, because if you really take a look at, you're going to have settings in the relays that are, connected to breakers and stuff operate much faster than IEEE 1547. So when you have something like this, you got to understand that, we're not in any one of the ISOs and RTOs. We're vertically integrated utilities. So over here, if you try to wait, for example, a low voltage right or some of these, they are set much lower, than some of the settings. So you have to compare those settings with the low voltage right through and all of that other stuff with our settings, right? So IEEE 1547, when you get it certified, if you want to do the islanding, some of your settings, even within the substation relay, are much faster than those. So those might actually, operate on the feeder much faster.
Great. And then there is another question from Sandeep. Have you considered breakers with grounding switch in lieu of grounding transformers to overcome the grounding problems you mentioned in the presentation?
No, I didn't, and the reason why I didn't is because when you have grounding transformer, I didn't do over here, but there are probably like 4 different other types of analysis that you have to do with this stuff. I haven't shown it over here. I have to finish some of the simulations, but a lot of people don't even talk about it. You got to take a look at fair resonance, right? You got to take a look at open phase. You got to take a look at line to ground faults and line to ground faults with these ground transformers. So the easiest way to do the solid grounding, because you want to make sure that this particular system acts as if it was a system as we know it today, right? The easiest way to do is do the grounding transformer. Somebody was saying, you can just put inductors over there and that would kind of resolve the problem. Yeah, but protection and control that's secure and reliable, it's a whole lot more complicated than anything else. Now, any microgrid can be like 5-6 miles long, and then that also has major impact on how you do protection and control analysis and everything else. So a lot of things that I see, they just focus on one thing, but you got to simulate about 6 different things if you, put grounding transfer just to make sure it's properly size. So even if you do something just for grounding, you got probably 6 other things that you have to worry about. And the easiest thing to do is with grounding transfer, based on what I have seen, to be honest. It doesn't mean that this doesn't mean that whatever I'm telling you is the only answer. This is just a answer or a solution that works, at least the one that we have seen. So I'm sure there are pros and cons to every, solution.
That makes sense. Now we do have a couple of other questions from Venkatesh. Says, as per literature suggesting that PG equals to PL, due to the perfect match, there was no frequency, then how dF by dt works, and then a frequency change almost negligible, but how dF by dt can pick up in your case.
Everything that I've shown you is literally a function of changes, right? And remember, when you have dF over dt, right, that's theoretical change, right? But if you have a field, right, everything in the field changes, right? So during the transition, dF over dt might be equal to 0, but it's very highly unlikely that dF over dt is going to stay 0 for a long time. Why? Because, I don't know if you're familiar with this, but every time when you go into islanding, right, you switch from grid to microgrid, right? And then when you switch from grid to microgrid, even before that switch, there is a different requirement from every load for reactive power, right? Why? Because the moment you switch, the voltage changes, right? Because the voltage inside the microgrid is going to be different than the voltage from the grid. And for every change in that stuff, what changes is the reactive power requirement, which means now you have to support that stuff. In addition to it, also your frequency source distance from the load is different. So yeah, in theory, right there at the second, PL might be equal to PG, but things are going to change within that. That's going to be not equal essentially all the time, right? Because that's how different loads react to changes in voltage and frequency. So even though at very moment, it might be equal, it's going to start deviating pretty soon. Everything that I have seen, we didn't just test it once, to be honest. We have tested this probably like 10, 20, 30 times at PL over PG. And I can tell you that I have had 0.0 kilowatts, I had 0.1, 0.2. Remember, at very, very low kilowatts, CT. PTs are really accurate because they're 0.5% or better, but CTs are not. So there's, that right there. But we had tested about 20 or 30 times within 0 to about 0.4 kilowatts PCC, and every single time it operated. Real life is a whole lot different than the simulations, and things that we have seen in simulations we have never seen in the field. So a lot of simulations that we have gotten for this transient stuff are totally not the same as real response in the field.
Sounds good. And looks like we have a bunch of questions here. I don't know, Alex, if you have a time limit or something like that.
Yeah, I don't have time limit. Just I'll answer every question. And if anybody has any other question, there's my email, and you can give everybody my phone number. I'll be more than happy to explain anything. Now, everything that I'm telling you is our experience up to this point. I'm sure there are many other ways to do some stuff. I can just tell you the reasons why we did some stuff. So I'll be more than happy to answer all of the questions.
That is great, because the system that was set up for the webinar, I think it automatically, the WebEx session will close at 2 o'clock. I haven't been through to 2 o'clock, so I don't know if it gives us a warning message or something like that. But before that happens, I want to give an opportunity for everyone to know that you can find Alex on LinkedIn. Alex, if you want to bring up a slide or something that has your email address and LinkedIn.
Okay, yeah. So the email, my email is the end of presentation. So there's more to this stuff. So let me put it. Okay, this is my email, right? And you can also, if you want, you can do this email too, if you want to. And my phone number is this. So this is my cell phone.
It's a U.S. number, so for people outside, please try with the +1 in the beginning of it.
Yeah. Okay. I would have +1.
Yep.
All right. There you go.
And you can also find Alex on LinkedIn, right? Alex, are you on the name
of
Alexander, the same name on LinkedIn, or?
Correct. So if you have any other questions, or I can just share, our experiences. And if anybody's ever in Charlotte, if you ever want to see the Mount Holly microgrid, there's a whole lot more that I didn't go over, but you're more than welcome. Just let me know, and I'll show you just about everything. You can see all of our screens. You can see just about everything that we have done at that place.
That sounds awesome. And for those who would like to see the slides and also to listen to this recorded session, we're currently updating our website, so we should have the slides available the slides should be available. Slides and the recorded session would be available at this link in a week of time, and also any previous sessions we had that are already recorded. So, Alex, if you don't mind, if you already send the slides to us, that's great. If you haven't, if you don't mind sending those to us via email, that would be great. I will upload them on the website. And,
I'll send them to you.
Awesome. And hopefully, I was thinking maybe we'll open a conversation section on LinkedIn, so that I see that there is a lot more questions here. But as I said, there is a limitation on the WebEx, right? So I'm hoping there will be an awesome conversation on LinkedIn with a lot of questions back and forth and answers too. So guys, please watch out for an email from us. We will share a link from LinkedIn for the LinkedIn conversation where you can post more questions to Alex. Yes, Gusan, the slides and the recorded session would be updated to that website, uploaded to that website in a week of time. And Alex, thanks a lot. Thanks a ton for your time and presenting this for everyone here today. We really appreciate it and enjoyed the session. We'll get in touch with you soon to see if we can maybe do a part two kind of a session since
Yeah.
there are some slides missing. Yep.
Yeah, just to let you know, what I didn't go over through is there's a whole lot more that I didn't go through, but I had over here section. We do have a DC coupled energy storage system. I know that's maybe a lot of people are talking about it. We have implemented this maybe about a year ago. We got some results, and it's up and running. I can definitely show you this section and anything else that you might be interested in. So thank you for having me. If there's anything else I can do for anybody, I'd be more than happy to. Send me an email, and then if you want to call me, by all means, I'll be more than happy to share anything that I didn't or answer any of your questions if I can.
That is awesome. Hey, thanks a lot, Alex. And Venkatesh, Gusan, Taif Muhammad, like everyone else who has been actively posting questions, please watch out for our email. We'll open a conversation on LinkedIn. So please feel free to share your questions there to Alex. Thank you, everyone. I appreciate everyone's time. You have a great day and stay safe.
Thank you.
Bye-bye.
Thank you, you too. Bye-bye.